Greetings to you all. This is teacher Cado de Gracias. Please, I ask you to subscribe to my channel. There's a lot of information I'll post here, but make sure you are the first to get it. So please subscribe, place that button of subscription and subscribe to my channel. I'm here today to present to you the basic concepts needed in practical calculations. A couple of days back, we had looked at steps taken when handling chemistry practical calculations, and we looked at a number of approaches. And after that, I left you with an exercise of which I was expecting you to get answers and also make some research. Those who tried, thank you very much. Those who never tried, don't worry. I'm going to provide you the answers today, and more so, I'm going to provide you with a lots of techniques. So I'll answer the questions step by step, and in so doing, I want to equip you with some techniques that would help you to answer even other moral concept practical calculations and even in theory. So at the end of this lesson, you will be able to answer a variety of questions that may be different from the ones I gave you the other time we are together. So today we are going to look at this. Today we are going to look at the basic concepts needed in practical calculations, and under this we are going to look at how to start from known to unknown. We shall look at basicity of acids. We are going to look at writing chemical equations using basicity of acids. We are going to look at using mole ratios to calculate moles of a solution whose concentration is unknown. We are also going to look at the basicity, using the basicity to find the formula of an acid. Then finally, we shall look at the common equations that are applied in chemistry practical calculations. In my last lesson that I left with you, we looked at how to analyze the practical extract, and we said this extract is very important. There's a lot of information I gave you concerning this extract, but today I just wanted to make a recap so that we move together. We also looked at how to handle practical results. We looked at how to identify consistent results, and we looked at how to register these results in a table and even those of the pipette. Here for the volume of pipette you are seeing 25, but as I taught you the other time, we write 25.0 cubic centimeters. But since this is just a teaching aid, don't worry much. But these are the results I left with you the other time I had a lesson with you. And these are the questions that I left with you, which questions I was expecting you to make some research and come up with answers. But as I said, we are going to answer these questions step by step, and in so doing, you're going to get techniques which will help you to answer even other questions that are different from these ones. Now let us start straight away with our first objective. This is how to start from known to unknown. Before you start your calculation, you need to know the volumes of the solutions that reacted. In this case, we are having Ba1, that is sodium hydroxide, and its volume that reacted was 25. The volume of Ba2, as you may see, that is HNX acid, its volume that reacted we calculated 12.45 cubic centimeters. Then also we said we should know the solution that is standard. In this case, sodium hydroxide was a standard solution, and its concentration was given as 0.3 molar. So the question was here, it was asking us to calculate the number of moles of Ba1 that reacted. So we know this information. We know the volume of Ba1 which reacted. We even know the concentration of Ba1 that was given to us. So starting this calculation is very simple. Now I'm going to go back to the section under that extract, that section of the practical extract, the one I showed you the other time. I've just picked a very small statement here. This statement, as you see above here, it is saying from 0.3 molar of sodium hydroxide. That statement there. That statement, as you may see it, it is trying to tell us the concentration of the standard solution. That one, that statement there, it is trying to tell us the concentration of the standard solution. So what does 0.3 capital M mean? Remember we said we start from known to unknown. So after knowing what 0.3 capital M means, we will be able to apply it and we calculate our number. So in this case, if you are in mole concept and you see any number attached to a capital M, maybe 0.2 capital M, 0.1 capital M, 1 capital M, 0.2 capital M, any number, wish any number. If it is connected with a capital M here, it means that you are having those number of moles containing in 1000 cubic centimeters to make a solution. So in this case, when we have 0.3, it means we are having 0.3 moles of Ba1 containing in 1000 cubic centimeters. Where have we got that statement? That statement, we have got it from that small section I've extracted from our procedures. So we are having 0.3 moles of Ba1 containing in 1000 cubic centimeters. That's what 0.3 capital M means. Okay, so after writing that statement, we need to go back and find out which volume of Ba1 reacted. In this case, the volume of Ba1 which reacted was 25. So if 0.3 contained in 1000 cubic centimeters, what about 25? Let us look at the side working down here. Side working, it is just down there. Let us look at that. So we have started by saying that 0.3 capital M means the number of moles containing in 1000 cubic centimeters. In this case, we are having 0.3 moles containing in 1000 cubic centimeters. Then what about 25? So here, the 25, we shall just cross multiply. We shall cross multiply 25 times 0.3, then divide by 1000. So we come up with 25 times 0.3 divided by 1000, and the answer we get here is 0.0075. So therefore 25 cubic centimeters of Ba1 contain 0.0075 moles. But I want to make myself clear, we don't use formulas in chemistry. In chemistry, we use statements. So examiners may not mark your formulas, or if they are to mark your formulas, you get little marks. So make sure you use statements as I've used mine here. So you start by saying 0.3 moles of Ba1 contained in 1,000 cubic centimeters. What about 25? You cross multiply, get 0.0075 moles containing in 25 cubic centimeters. So therefore, the moles of Ba1 that reacted, they are equal to 0.0075 moles. So those are all statements. We have not written any formula. This side working was just to guide you and help you know what I was doing there. So I advise you always to use statements. Avoid using formulas. Formulas are not needed. Okay, let us continue. Let's continue. Okay, now we want to look at calculations involving a solution whose concentration is unknown. Like for example, if you look at our statement here, if you look at our practical extract or statement here, they're trying to tell us what Ba1 is and what Ba2 is. But in this case, they are silent about the concentration of Ba2. Ba2 concentration was not given, but for Ba1 they gave us 0.3. That's why we are able to use it in our calculation. But for Ba2 we know nothing concerning concentration. So we are looking at how we can use different approaches to calculate or to do calculations that are involving a solution whose concentration is unknown. So here there are three major concepts or approaches which we should always keep in our mind when we are going for a calculation containing a substance whose concentration is unknown. 1. You should ask yourself, are you able to write the equation of reaction? Equation, that is the approach number 1. Are you able to write the equation of reaction? For number 1. Are you able to identify the molar ratio of the reaction? Are you able to identify the basicity of the acid that is being used? So if you have answers or one of the three answers with you, then calculations involving a solution whose concentration is unknown is going to be very easy. So examiners will always give you one of the three. They may give you one of the three, or they may give you two. So it's up to you to check which approach you are going to use. So before you start any calculation involving a solution whose concentration is unknown, check to see whether any of those three is provided. If any of the three is provided, then calculations are going to be easy for you. Okay, let us continue. And now we have looked at the three approaches or the three approaches which we may use to calculate or to do calculations involving a solution whose concentration is unknown. Now in this case, they have provided us with the molar ratio. The question is simple here. Calculate the number of moles of Ba2 that reacted. And in that case, they have provided us with the molar ratio. The molar ratio is there. It's just right there. So calculations are going to be easy for us because the molar ratio, we have it there. We are having a molar ratio of Ba1 to Ba2. It is 2 to 1. So our calculations here are going to be very easy. Remember, we said we start from known to unknown. They have given us molar ratio. What else do we know? We know the number of moles of Ba1 that reacted. We have calculated and we have got 0.0073. We calculated and we got those number of moles of Ba1. So which means in our calculation, we are going to compare moles of Ba1 that reacted with those of Ba2 that reacted, but we shall start from what is given to us or what is possible to be applied. For example, in this case, we had looked at the 3 ways we can use. Okay, let us make a flashback here. We looked at those 3 ways that in any calculation involving a solution whose concentration is unknown, one of the 3 must be provided. For us, they are provided as the molar ratio. So that is going to be our starting point. If you are going to use the equation of reaction, that is still going to be your first approach. If it is basicity, you'll begin with basicity. Okay, for our case, they have given us the molar ratio. So we start from known to unknown. Let us go straight and we look at our side work here. What is being given to us if we go to our side work here? Ba1, Ba2. They have given us Ba2, the moles of Ba1 which reacted, they are 2 moles. Then moles of Ba1 that reacted, they are 1 mole. Then what about the moles which we calculated? Remember, we calculated 0.0075 moles. So it is a matter of cross multiplying. Get 0.0075 multiplied by 1, multiply by 1 here, then divided by 2. So the end result of our answer is 0.00375. So that is our side work. When we go back to making statements here, you're going to start from what you already know. So we have 2 moles of Ba1 reacting with 1 mole of Ba2. Then what about the what about the 0.0075 moles? We cross multiply as I've already told you, and when we cross multiply, as you see the multiplication there, we shall come up with 0.00375. So therefore, the moles of Ba1 that reacted, I mean Ba2, in this case we are dealing with the Ba2. For Ba1 we have 0.0075. For Ba1, I mean Ba2, we have calculated 0.00375. Ba1 is 0.0075. Ba2 we have calculated 0.00375. I think we are together. So those approaches, as I have shown you, they are the ones we use if we are to calculate a solution whose concentration is unknown. And I said, and I repeat myself by saying, never use formulas. Never use formulas. We use statements. So I have used the statements here to calculate the number of moles of Ba2 that reacted. Okay, let us continue. Now there is our third question here. There is our third question, which was asking us our third question was asking us to calculate the basicity of the acid, that is HNX. The third question was asking us that. But this question is very cheap, very easy. But it's something I want to pass on to you, which will help you handle any question related to that. Okay, so let us first look at Besiste. We look at some concepts in Besiste which will help us answer any question that could be coming from this area. Now, what do we mean by basicity of an acid? Basicity of an acid here simply means the number of moles of ionizable hydrogen ions in a molecule of an acid. For example, we have HCl. We have HCl here. We have HCl, this one. You can see it is having one hydrogen. HCl has, or hydrochloric acid has only one hydrogen in one molecule. So its basicity is 1. Okay, let us move on to sulfuric acid. For sulfuric acid, it has 2 moles of hydrogen in one molecule. So therefore its basicity is 2. Okay, for phosphoric acid, it has 3 moles of hydrogen, and therefore its basicity is 3. So therefore, basicity simply means the number of moles of ionizable hydrogen ions in a molecule of an acid. However, there are some acids that are having many hydrogens but having few basicity. That is, they may have like 3 hydrogens, but when their basicity is 1. For example, let us look at ethanoic acid. Ethanoic acid. Okay, that is ethanoic acid. Let me write it more better. Okay. It has a 3 on H and also C, or there are 2 O's here and the H. When you look at that acid, it looks like it has 4 hydrogen atoms in it. But not all the hydrogens here contribute to it being an acid. Here, what makes this acid an acid is this hydrogen here, and it is 1 hydrogen. So therefore its basicity is 1, which means in a solution state the other 3 hydrogen do not, these 3 here, these ones, they do not ionize. They don't ionize. It's only the hydrogen which is here which ionizes in a solution form, and therefore its basicity is 1. It is not 4, it is not 3, but it is 1. Okay? Okay. So I think you've got something here. Let's move on. Now we want to look at application of the system in writing correct formula and equations. Here basicity provides us the valency and the oxidation state of the radical in the acid. Some acids, some of the solutions provided to us in a practical may be having their real formula, while others may be having some unknowns. But even if you have any unknown in an acid, for example the radical, we shall be able to tell which valency that acid is, or which oxidation state that acid is. Let us look at these 3 examples. We have hydrochloric acid, hydrochloric acid there. I already said it has one hydrogen in it, so therefore when you look at it, the valence of the chloride moves to the hydrogen and that of hydrogen moves to the chloride, and we come up with the formula HCl, having one valence, one valence. Remember, those one valences are not represented in a chemical formula. That's why here we are just writing HCl with no 1,1. Okay, now let us move on and we look at another acid. Let's look at sulfuric acid. Sulfuric acid here, the sulfate has two, the oxidation state is 2, the valence of that sulfate is also 2. When you cross it and you cross that of hydrogen, we end up getting the formula H2SO4. I think you can see that the valence of the radical in the acid is passed on to the hydrogen. So therefore, we come up to that formula. Okay, let's move on to phosphoric acid. With the phosphoric acid, you may see it is having a valence of 3, the hydrogen 1. So the 3 goes to the hydrogen, the 1 comes to the phosphate. But remember, we don't write that 1. So therefore, the formula for phosphoric acid becomes H3PO4. So here there is something common we need to learn here, or there is a concept we need to learn here. The basis of any acid represents the valence of the radical. Look at the first HCl acid, how it is formed. The valence of the chloride here is 1, and the oxidation state of the chloride here is Cl minus. Minus 1 is the same as minus. Even if you don't put 1, it's already minus. When you go to sulfuric acid, this one here, if you go to that, you're going to see that the valence of the sulfate is 2, and also the oxidation state of the sulfate is 2 minus. It is 2 minus. Let's move on to the phosphate. The valence of the phosphate here is 3, and its oxidation state here is 3. So if you are writing any formula or any equation involving these acids, so long as we know their basis state, we shall be in a position to write the products of the reaction, and therefore the equation will be balanced properly. Okay, let's move on. Okay, so here we are. Remember, we are looking at how we can apply basis state to write correct formula and even writing equations. So here, consider these equations. We have 1, 2, 3 equations. If we look at the first equation here, that is the equation between sodium hydroxide and hydrochloric acid. I think you can see it. When you look at that equation, you are going to find that the molar ratio between sodium hydroxide and the acid is 1 to 1. The molar ratio there is 1 to 1. I think you can see it. When we go the other side of the products of the reaction, you are going to see that we are having sodium chloride and water. Let's move on. We look at the second equation here with sulfuric acid. You are going to see here that the molar ratio here is 2 to 1. As you may see, the molar ratio is 2 to 1. That of phosphoric acid, it is 3 to 1. Now you may be asking yourselves, why am I using sodium hydroxide to react with the acids and getting such ratios? there's a technique we need to learn here. Sodium hydroxide is just a representative of the bases we use in our practical. Remember, in our practical, we react acids with bases. But you know most of the bases are insoluble in water. And for us, we use solutions. We don't want substances that are insoluble. So we use sodium hydroxide simply because it is a soluble base. Similarly, when you look at sodium hydroxide and potassium hydroxide and ammonium hydroxide, I think you know the formula of those compounds or those bases I'm talking about. Those bases have similar balancing numbers. So in an exam, reacting bases with the acids, they may bring any of the three compounds I've mentioned. But the balancing numbers or the molar ratios are the same. And how do we get these molar ratios? They come from the basis of the acid. Let us look at the first one with sodium hydroxide, the first one we began with. You are going to see that sodium hydroxide, you are reacting 1 mole of sodium hydroxide with the acid, which acid is having a basicity 1. Altogether? Okay. When you go to the second with sulfuric acid, you are going to see that 2 moles of sodium hydroxide are reacting, and the basicity of sulfuric acid is 2. The molar ratio is 2 to 1. Okay, let's move on to sulfuric acid. Here you're going to see that there are 3 moles of sodium hydroxide reacting with the 1 mole of phosphoric acid. There are 3 moles of sodium hydroxide reacting, but also the basicity of phosphoric acid is 3. So those moles of sodium hydroxide you see from the first one, which is 1 mole, the second one, which is 2 moles, and the third one, which is 3 moles, they are just representing the basicity of the acid. Okay, let us move on to the other side of the equation where we are having reactants. For the first equation here, we are saying that sodium, we are forming sodium chloride. The balancing number here, I mean the valency here, is 1. That of sodium is 1 and that of the chlorine is 1. So the 1 on sodium in sodium chloride is representing the basicity of HCl, and you are seeing we are forming 1 mole of water. Okay, let us move on to this one. When you look at the product we are getting here, we are getting sodium sulfate, and the valence of the sulfate has gone to the sodium, and that 2 which is on the sodium is also representing the basicity, and on the water you are also seeing a 2 there. Okay, let's go to this. That of phosphoric acid, you are seeing a 3 on sodium and a 3 on water. You have 3 moles of water. So as I said in my introduction here, I remember I was talking about how we use acids to write correct formula. Are you seeing that the basicity of the acid is matching with the oxidation state of the radical within the acid? For HCl, the oxidation state of the radical chloride is 1, that of sulfate is 2, that of phosphate is 3. Are you seeing how they are matching? Okay, let's go back to our questions. Okay, so now the same is applied here. We are seeing sodium chloride the valence of chloride has been passed to the sodium. You are seeing sodium sulfate, the valence of the sulfate is passed on to the sodium. That of phosphate is passed on to the sodium. Now let us look at a general equation to summarize all this we have been looking at. Okay, now we can come up with a general equation like this one. Where you see N, that N is representing the basis of the acid. If we begin with sodium hydroxide here, we are going to see an N. That N is representing basicity. When you go to the acid, there is an N. That N is still representing the acid. When you go to sodium X, the N is still representing the basicity. When you look at water here, it is having N. That N is also representing the basicity. So if we know the basicity of an acid, it is very easy to write the equation of reaction. Just use the basicity to write a correct formula and also to balance your equation. So if we know the basicity of any given acid, we shall be able to know the valence of the radical in that acid. We shall be able to know the oxidation state of that radical in the acid. So we have seen this general equation trying to summarize everything we have been looking at here. It is just a summary of these equations. Okay, I think you've picked something. Okay, let's try to move on. So that is our general equation. We have looked at it. I think you've noted something. Let's continue. Now we go to our question. Question C is asking what is the basicity of the acid HNX acid. This basicity, the basicity here can easily be calculated from the molar ratio. The molar ratio, fortunately, is provided to us. They have told us the molar ratio of Ba1 to Ba2, which is sodium hydroxide to HNX acid, is 2 to 1. It is 2 to 1. But even if we don't know any for the basicity, so long as we know the number of moles of sodium hydroxide reacting with the acid, those number of moles of sodium hydroxide reacting with the acid, they will be representing the basicity. So therefore the basicity of HNX acid is 2. If you try to write the formula will be our formula, if you try to substitute in, we shall have our formula as H. Okay, let me try to write it here. We shall have H 2 X. So that is going to be the formula for the acid. How have you got the 2? The 2 is got from the molar ratio between the sodium hydroxide and the acid. And that molar ratio was provided to us. We don't need to find it. It was provided to us. I think that one is clear. We have just substituted the N with the 2. Okay. Now there is another alternative we can use to calculate the basicity of the given acid. Here we just needed to calculate the number of moles of each of the substances reacting. So in this case, we have the number of moles of sodium hydroxide. We calculated 0.0075 moles. We calculated that. Okay. So we calculated those number of moles, 0.0075 moles. Do we know about the moles of Ba2? Yes. we calculated those moles also, and therefore we got 0.00375. So it's a matter of comparing the two. So we shall get molar ratio of Ba1 to Ba2. Molar ratio of Ba1 to Ba2. What is Ba1? Ba1 is sodium hydroxide. What is HNX or Ba2? Ba2 is HNX. So just write your moles. You have on sodium hydroxide, you have 0.0075. You have those moles on sodium hydroxide. Then on the acid, we are having those number of moles. So if I want to get the molar ratio, it is a matter of dividing the smallest throughout. What I will do, I will just divide throughout by the smallest, as you see here. As you see there, we are dividing 0.00375 throughout. If we do that, we are going to come up with a molar ratio of 2 to 1. So that molar ratio we have got there, the molar ratio which is on sodium hydroxide in this case is representing the basis of the acid. I think you have got that. So therefore, the basis of the acid from our calculation is 2, because we are having 2 moles of Ba2 or 2 moles of sodium hydroxide reacting with 1 mole of Ba2 or HNX acid. So the basis is 2. Okay, think you are following. Let's move on. Now we have this last question. It is asking us the relative atomic mass of X. They are asking us the relative atomic mass of X. In this case, we just need to first get the formula of HNX. When we substitute in the basicity, we shall come up with H2X. So we shall compare relative molecular mass, the relative molecular mass with the molar mass. So relative molecular mass simply means we calculate the total of the atomic masses, then we shall be able to compare it with the molar mass, which is 98. If we try to calculate, we are going to come up with this answer where X is equal to 98. Okay, sorry, it is 96. X is 96. We have already seen it. Now let us look at common equations applied in chemistry practicals. There are 2 very important common equations that may be applied in our chemistry practicals. The first one is an acid reacting with a base. I think we know the product when you look at equation 1. When an acid reacts with a base, we get a salt and water. For example, if we are having hydrochloric acid reacting with the M hydroxide, we get M chloride plus water. Here M is representing any metal. Depending on the need of the examiner, they can give it to you as a correct symbol, or they can just give an unknown, as in this case. So if they bring an unknown, don't be confused. Just write your equation, know the oxidation states of the radical in the acid, know the valency of M. Of course, the valence of OH is 1. So if M is not given, we shall be able to write correct formulas. So you can write correct formulas and go ahead to balance your equation. So in this case, the valence of M is 2. That's why we are having M hydroxide with a 2 on hydroxide. If you look at this, there's a 2 on hydroxide, meaning that M is in valence 2, or M has an oxidation state 2. When we come to the chloride, there on the chloride, you are having M chloride with a 2 on the chloride, meaning M is in valence 2. So if the valence of M is stated, then writing the formula becomes simple. So if they tell you that M is a metal in group 2, a metal in group 3, a metal in group 1, or M has a valence of this or oxidation state, that you apply that to write the correct equation of reaction. So therefore, when we are in a practical, expect to find questions on acid-base reaction or acid-base titrations. Another one is carbonates reacting with acids. When a carbonate reacts with an acid, we get a salt, water, and carbon dioxide. We get a salt, water, and carbon dioxide. Still, M can be hidden, and they just call it an unknown. So you just apply the knowledge of balancing, the knowledge of writing correct formula, and you write your equation of reaction. So why do we need equations of reactions in a mole concept? When you are to apply equations of reaction here, they will help you get the molar ratios, which molar ratios will help you to calculate moles of a solution whose concentration is unknown. So they may not give you the molar ratios, they may not give you the basicity, but they might just give you the formula of the substances reacting. Then for you, if you are to write the equation of reaction and come up with the balancing numbers, then you'll be able to get the molar ratios there, which molar ratios will enable you to calculate the moles of the solution whose concentration is unknown. So after covering all that, I think I've given you enough. Try to put them in practice. Look for questions, look for past papers, apply that knowledge. I think you'll get the best out of this lesson. I want to thank you for attending my lesson and watching my presentations. I continue ask you to subscribe to my channel. Next time we meet, I'm going to bring something very special, and make sure you don't miss our next lesson. The next lesson, we're going to look at something new. We have completed anything to do with mole concept. So next time, expect something to do with another thing, and probably we are going to look at rates of reaction. We shall look at it from A to Z. So make sure you are present. God bless you. Thank you for listening to me.